Hello friends, I am Dr. Bharat Deshpande from BITS Pilani University, and I am going to take you through this course on data structures and algorithms. To begin with, we will just try to look at the course title, which is data structures and algorithms, understand what it means and see what we are going to do in this course. For most of us, when we are introduced to computers, it is either through using them as some application, or to more advanced users, we use computers as computing machines. And the first step that we do towards this is to look at or learn to write programs. So, probably at school level we start writing programs. Programs are essentially something that computes something. Like it could be a program to compute average of numbers, it could be a program to compute roots of a quadratic equation, or could be a program to do maybe something more complex. So, what essentially these programs are? They are meant to compute something, or they are meant to solve something. So, you have a problem and you intend to solve it. So, that is the first part of writing down a program, is there is a problem and there is a solution to a problem which you know, and a program is just a representation of that which a machine understands. The other subtle factor that is involved is the data that you are going to handle. If you are going to compute averages, then you have to probably work with integers, you have to work with decimal systems, so forth. So, it is the data that you want to handle and the data which you would like to represent in a computer. So, these two key things are what underlies beneath a program, and that is what the course title is about. Data structures are something that deals with how we are going to represent data in a machine, and algorithms are solutions to the problem. So, that is a brief introduction to the title of the course, which is data structures and algorithms. So, that precisely is the first slide that I have put down, which says that algorithm is a step by step procedure for solving a problem in a finite amount of time. So, that is a very crucial statement, that your algorithm has to solve a problem in a step by step manner and should be able to finish its job in a finite amount of time. Another factor to be emphasized is that an algorithm is supposed to solve all instances of a problem. What does that mean? Suppose we take a quadratic equation, we know how to find the roots of it. The procedure to find the roots of a quadratic equation, we know, does not depend upon a particular instance of a quadratic equation. So, that is the first key point which we are going to look at, is an algorithm is supposed to solve problems, all the instances of a problem. Data structures, as we said, is just a systematic way of arranging data which can be understood by machines, and programs are essentially nothing but algorithms and data structures put together. So, that is a sort of a brief introduction to the title of the course. So, typically in real life we are faced with problems. When we say we are faced with problems, we typically know what our input is. For example, if we want to find an average of numbers, then we know we have a sequence of numbers whose average is to be computed. So, if I look at this, so you have specification part. So, this is something that we know beforehand, that is the input that we want to handle, or we want to do something or compute something or infer something from the input. What we also know is the output that we intend. That is, if we have given a quadratic equation, we know we want to find the roots of the quadratic equation, or if you are given a sequence of numbers and you want to increase them in arrange them in increasing order, we know exactly what input, given an input, what output we expect. What is important is the part which is going to be an interface between the input and an output, and that is precisely what an algorithm would do. For example, your input sequence here is an arbitrary sequence in an unsorted manner, and output that we expect is a permutation of this input which is in increasing order. Right. So, if you notice, the output that we want is in increasing order. What we intend to do or find is the middle part, which precisely given this input will give us the output that we expect, and that precisely is the next slide, where we have a specification of input, you have a output, and algorithm is a solution to our problem, or algorithm given an input finds a specific output that we expect from the input. So, algorithm is something which describes actions on an input sequence. Again, in practice we know that given a problem and the solution that we want to find may not be a unique solution. It has two key points which one has to understand here. Let us look at a very simple example. Suppose you are given a map of a city and you are expected to, and you are given a point A where you have to start and reach to a point B. So, you have a map of a city and you know your source which is a point A in the map, and you know your destination point B, and the problem is to find a path from point A to point B. Now, we know in practice that there can be several paths from point A to point B. Right. So, the solution to a problem may not be unique. That is one of the first. So, you can have many solutions to a given problem. Another key observation is that I can look at the same problem and modify it a little. Suppose I know the same scenario, you have point A and you want to reach point B. Now, suppose you have added information that point B lies to the south of point A. Now, the first problem and the second problem, though look similar, are different, in the sense in the second problem we know something more about the problem. So, probably the solution that we seek might be something which can use this additional factor, and probably the solution that can be achieved would be in some way better than the first solution. And this is another key area that we are going to tackle in this course. That is, if we have multiple solutions to a problem, how do you decide which solution is a better? Also, emphasizing again, if we have a problem, the algorithm is expected to solve every instance of the problem. For example, if you want to sort a sequence of integers, then it should sort sequence of random numbers, that is numbers which are in random order. So, there are two key points which I would like to point out. One is the algorithm that we are proposing or trying to achieve or trying to find should be repeatable to any instance of a given problem. So, for example, the solution which you find, which allows you to find a path from point A to point B, should be repeatable to an instance where you have a source at point C and destination at point D. That is what the repeatable arguments would mean. That is, the solution that we propose should be repeatable to a similar instance of a problem. And correctness is an issue which is not very easy to handle, but one should be always careful that the fact that the solution that we propose to find actually finds what we wanted to achieve. It is something which is not very easy to deal with, but we will try to understand this as we go further in the course. Is what do you mean by correctness? So, that brings us to the first important question that this course is trying to address, is what do you mean by good algorithm, right? We have seen that a problem can have different solutions. Different solutions are going to be represented by different algorithms, and obviously one has to choose a problem or an algorithm which is better. So, what is this better? Is that we are going to try to quantify. So, when we are trying about a solution, we also know at the back of mind the solutions are something that we are going to try to implement or try to solve using machines. So, the goodness or the betterness metrics that we are going to use should use, or it should be in terms of the machines that are going to implement this applications. So, when you we know when we want to write down a program, two things are important. One is the actual running time, that is the time required to execute your program, and the space that is used or the memory that is going to be required to execute the program. So, these two key factors are going to be the determining factor in deciding an algorithm which is good or bad. Now, how do you measure these resources, right, whether it is running time or the space used? So, let us look at the problem of sorting numbers. Now, suppose you have a sequence of numbers that you want to sort and which has say 10 numbers, and you try to sort this sequence of this 10 numbers. If I look at the running time and if I look at the storage that is required, would be proportional to the numbers that I have in the sequence. If I increase this to 25 numbers or 26 numbers, the running time as well as the resources used in terms of storage can vary. So, our resource usage is always going to be measured proportional to what is the size or the instance of your problem. So, that is a key factor or an assumption that we are going to have, that resource usage is always going to be measured as proportional to the size of the input. Okay. That brings us to how do you measure the running time. So, as we said earlier, one can actually write down a program for a solution, actually measure the running time, vary the inputs. Instead of sorting a sequence of 10 numbers, try to sort a sequence of 20 numbers, change the order of the sequence, try to make them random choices. So, keep on experimenting with it and then try to use system calls to measure the time. That is sort of a brute force way of looking at things, or a very rudimentary way of looking at things. There are obvious disadvantages of this experimental study. That is, one needs to implement first before deciding which algorithm is better. What that would mean is, if I have 10 solutions to a problem, to understand which is better, one will have to implement them, experiment with them, and then probably decide which is better, which probably is going to be quite time consuming. And critically, if you need to compare two algorithms, they should be implemented on the same platform, that is using the same hardware, same software, same sort of machines with similar speeds and so on. So, as we see, there are quite a few limitations with working with experimental work. So, what we need is to understand which algorithm is better without actually going through the implementation part of it. That would really save a lot of time and would really be a pointer of really which algorithm is better. So, what we need is an analytical model which is going to be a general method and would require a few approaches. So, rather than looking at algorithms, what we are going to look at is algorithms in as a high level description of an algorithm, and which takes into account all possible inputs and which is going to be machine independent. That means, what you want to understand is purely the computations done by your algorithm independent of the machines that you are going to use. To do this, we are going to use a particular language which is called a pseudocode language. So, the algorithms that we are going to propose and try to study without implementing, to put them in a step by step manner, we are going to use a language which is called a pseudocode language. So, it is a mixture of natural language and high level programming languages that allows us to express the main idea without actually working, without really worrying about the syntax of a programming language. So, there is a simple example of a pseudocode which is basically to find a maximum of n numbers. So, what is given is a sequence of n numbers which we are going to represent in an array. Say I have a sequence of numbers So, what you have is a sequence of numbers which is stored in an array, and the problem is to find the maximum of these numbers. The simple solution is you are going to scan the sequence from left to right and adjust the max as we scan the elements. So, we will start with the first element of the sequence. We have not seen any other element till now. So, the first element that you have seen in the sequence we will assume is a maximum element. We will update our knowledge as we go ahead scanning more elements. So, that is the first step that we are doing. So, we are initializing our max to the first location of the index. Now, we have a loop which is going to scan the elements from left to right one by one in a sequence, and as it scans the elements it updates the maximum of all the elements it has seen up till now, right. So, as I varies from 1 to n, I equal to you already initialize it to max to 8. Now, as we move here we compare ai with the current max. In this case our current max is 8 and 7 is less than 8. So, our current max remains to be 8. So, we are not going to modify our current max. Then we move to the next element of the sequence, compare it with the current max is 8, 9 is bigger than 8. So, in this case your current max is going to be updated to 9 and so forth, and as we scan all the elements this procedure or this algorithm is going to return the maximum of n elements. So, pseudocode as we see is basically a combination of natural languages and high level programming languages without getting into the details of the syntax of programming languages. It allows you to express your ideas in a structured manner. So, most of the course that we are going to throughout the course mostly we are going to deal with this pseudocode language. So, our procedures we will mostly try to use this language of pseudocodes. Yes, so pseudocode, this standard assumptions in a pseudocode are you are going to use mathematical symbols to describe numerical and Boolean expressions. A left arrow is going to be used for assignment, equal is going to be used for the equality relationship, and like in this case we are going to use function names to indicate what the program is going to do, and these are going to be the parameters for this function, right. The function here is max, and the parameters for the functions are an array A of size n. Right. So, here what you have is precisely the algorithm name, where in the earlier slide we say it was max, the parameters were the name of the array and the size of the array. In general you could have more than 2 parameters or 3 parameters. So, that is just the structure of a pseudocode as we are going to use in this particular course. Before we try to define or look at the analytical model that we proposed, that we want to evolve, we look at some basic assumptions that we are going to make in this course. So, the individual statements that we are going to have is going to considered as unit time, which is not going to be applicable for function calls and loops. So, in this particular example, if I look at this particular statement, that is basically a loop. So, according to our assumptions, we are going to assume that this does not, we are not going to look at the time that we are going to require to execute this particular expression. Whereas, an expression like this is going to take us 1 unit of time. It is an assignment to a variable which is current max. An assignment like this is going to say is going to take 1 unit of time. A comparison where we are comparing AI with the current max, we will assume takes 1 unit of time. So, that is the first assumption. Individual statements will be considered as a unit time, not applicable for function calls and loops. Individual variable will be considered as unit storage. Again, if I go back to my example of finding maximum, to find the maximum of a number we need a variable which is called current max. So, we will assume that this particular procedure requires 1 variable other than the, so the memory requirement or the storage requirement for this particular algorithm to be executed will be exactly 1, which is that we need a space for 1 variable. So, when we consider algorithms and the space usage, we are going to neglect that space required to store the input elements. So, we will assume that the array A is already in the memory, and what is important is how much extra memory is required to execute the algorithm. In this case, that precisely is only 1 variable location. So, individual variable will be considered as unit storage. We are going to refer to this as algorithmic complexity. The model that we are going to try to propose is called a complexity model. Before we actually again define our model, we look at what precisely are we looking at and what is that we want to abstract or try to model. So, let us look at a very simple straight line program where we have 2 inputs y and z, and we want to compute x, which is y star x plus z. Let us look at what is the time that is going to be required to execute this program and the memory that is going to be required to compute this. So, to compute x, we are going to require to execute this statement, which will take us 1 unit of time, and followed by another statement which is going to take us another unit of time. Correct? So, this particular straight line program, which is just 2 expression evaluation in sequence, will require 2 units of time, and it requires only one additional variable, which is x. So, it will require only 1 unit of storage. So, very simple. This particular straight line program requires 2 units of time to compute x and would require only 1 unit of storage. We will say that it requires constant unit of time and constant unit of storage. As we probably see, the next slides would be more insight into what really we mean in terms of constant unit of time and constant unit of storage. Let us look at a little more complicated example in which you do not have a straight line program, but you have a loop. So, in this particular example, and the array A and the size of the array A, which is n, are input. As we have already said, we are going to neglect this particular we are going to neglect the area, the storage that is going to require to store the input. What we are interested is the storage that is going to be required to execute the program. So, we have the first assignment, which is going to take us 1 unit of time. So, already we have to initialize j, or j is assigned value 0, which is going to be 1 unit of time. This particular statement is a while loop. So, we are going to neglect this. Now comes to the execution of the loop. In this loop, we have one computation which is multiplying aj with itself. Then we have another computation which is going to be bj, which is nothing but adding aj plus the index to it, and we are executing, we are incrementing j at the end of the statement. So, this while loop has precisely 3 computation steps. Whether your computation step is going to be a multiplication or a addition, we will assume it both takes 1 unit of time. We will call. So, what we are really looking at is how many computations precisely your algorithm will require to execute the program, or will to execute the algorithm. Now, this 3 particular steps are going to be repeated for all values of j. Right. So, as j goes from 0, we are going to do it 3 times. As j equal to 1, we will do this another 3 times, and up till n minus 1, we know j is less than n. So, j will be n minus 1. So, we will do it 3 more times. So, this particular computations are going to be repeated n times, that is 0 to n minus 1 times. Therefore, we look at that the number of computations that we do are, this all together is 3n, and this is another one. So, 3n plus 1 units of time, and it is going to require a variable which is j and an auxiliary array which is b, which is of the same size as a. Right. So, this n comes from the fact that you have an array a, which is an auxiliary array required to store this particular value, and the size of the array is same as the size of a, which is n, and you have additional variable j, which will require another unit of storage. So, this particular algorithm, as we see, requires 3n plus 1 units of time and n plus 1 units of storage. So, we say that this time is proportional to n and storage is also proportional to n. Now, we understand better example 1, in which we said that this particular algorithm requires constant unit of time and constant unit of storage. That means, the time required and the storage required is independent of the size of the input, whereas in this particular example the time required as well as storage required depends upon n. So, we say it is proportional to n. Let us look at a little more complicated example, in which you have now, instead of a single loop we have two nested loops. So, we have a loop here and there is a nested loop inside this loop. So, we have an example of nested loop. Let us try to analyze both time as well as the space requirement for this particular example. Again, we will assume that input is already there in the memory. So, we know array A of size n is already there in the memory. Before computing exactly number of steps that we are going to require, let us try to imagine what is going to be sort of nature of this particular number. Right. So, rather than looking at precise number, in this case we are trying to approximate some sort of order for this number. Now, let us look at two while loops. Now, if I look at this while loop, this is going to be executed, we know n times. J is 0, 0 to n minus 1. So, this will be executed n times. So, this particular assignment k equal to 0, we know is going to be executed n times, because this is executed every time the outer loop is executed. Now, we have an inner loop. Now, this inner loop is going to run for every value of j. So, if I write down, so you have j which is going to be say 0 initially, and for each j equal to 0 we know k will vary from 1 to k will also vary from 0 to n. Next time when j equal to 1, k will again vary from 0 to n, and so on up to j equal to n minus 1. This also is n minus 1, sorry, excuse me for that, and k also will be 0 to n minus 1. Now, this gives us a better picture of the particular algorithm. So, for each value of j, we are going to execute these statements this many times. So, if I look at, so now, so for every j we are going to run this n times, and j itself is going to vary n times. So, the number of computations or number of times at least the loop is going to be executed is going to be n squared, right. This n multiplied by this n, right, or number of iterations that we are going to have in this particular algorithm is going to be of order n squared. If we want the precise number of this particular complexity, then we can actually now write down the precise expressions. Right. So, this is going to be 1 unit of time. We know this will take n, already written. Now, we know this is going to be run twice. So, this is going to require 2 units of time, and we are going to run this n squared times. So, this will give me a factor of 2 n squared, right. This is going to be executed twice during every iteration of the algorithm. So, the number of times this is going to be computed is going to be 2 n squared, right. So, if you write down the final expression, you will get 2 n squared, then plus this n. These two statements are outside this loop, but inside the main loop. So, this will be again executed 2 n times and plus the first one. So, what we observe is that the number of computations this particular algorithm is going to do is 2 n squared plus 3 n plus 1. On this side, we had just sort of, without working out these details, predicted that the leading term of this expression is going to be n squared, and this is going to be very crucial in our understanding of complexity is, rather than working with precise expressions, can we capture this in a single order expression. One can similarly work out precisely what is the units of storage this particular example is going to be require. Yeah, let us look at more complex example than what we have been seeing up till now to understand what we are trying to measure. So, let us look at an example. Something that we are going to study in detail in this course is input is a sequence of numbers which is given in any random order, and the output that we want is the sequence in increasing orders. So, it is permutation of input numbers in a particular order that we want. The algorithm that is going to achieve this is the sorting algorithm. So, you have got input which is sequence of numbers and output which is rearrangement of these numbers in a particular order, and your algorithm is the one which achieves this rearrangement. As already seen earlier, the correctness requirement of the output means that for any input sequence, for any instance of a problem, the rearrangement that we want is achieved by using this particular algorithm, or this algorithm solves every instance of a problem, just rephrased otherwise. What we want to understand in this case is what do you want to compute here, or what is the number of steps that this particular algorithm is going to do to achieve this rearrangement. So, it depends on two factors. One is obviously the number of elements that you have in the sequence. So, instead of 5 numbers here, if I have say 10 numbers or 15 numbers, then the running time is going to depend upon the size of the input that you have. Also, we have also seen this earlier, is whether we have more information about the input sequence. This is similar to the problem of finding a path in a map. As we said, if we have point A and point B in a map and we want to find a path from point A to point B, and we know that point B is the south of point A, probably the way the solution is going to evolve is going to be different if we had no knowledge about this. And similarly, in this case, if you have some more knowledge about the sequence, whether your algorithm can take advantage of it and whether your number of steps that you are going to do is going to depend on that. If you look at the earlier examples, in this case, the number of steps that if you recollect, we had calculated, it was I think probably 2n squared plus 3n plus 1. If you recollect this, the number of steps that this algorithm computed was precisely this. This was independent of what size, what order, or what is the arrangement of these numbers. Right. So, whatever input A, the number of steps was always going to be precisely this, that is the number of steps that we have in an algorithm does not depend upon precisely what the input is. Whatever input, whatever order of input, number of steps is precisely 2n squared plus 3n plus 1, which is not the case in the sorting example. The sorting examples, your number of steps that you might require to solve the problem might be different for different arrangements of the sequence of numbers. So, if you look at the 4 examples that we have seen, if you want to summarize them, we have seen that running time or the storage, it can depend upon the size of input, In the first case it did not depend, and we said so it takes a constant amount of time. In the second case it depended linearly on input size, that is we had n elements, we had 3n plus 1 computations, space requirement was n plus 1, whereas in the third example it was of order n squared, it was 2n squared plus something. And in this particular case we have not yet computed, but we have observed that number of steps required to sort might be different for different arrangements of numbers. So, these all ideas we are going to try to abstract into a model and into an analytical model. So, that precisely is the purpose of what we are going to do is what is called order notation. That is, we are going to try to capture proportionality. If you recollect, we said 2n squared plus 2n plus 1 is something captured by n squared. So, we really did not have to write down the expression, but we could actually capture the highest degree term in the expression, and that is what we are going to try to do, is we are going to try to capture proportionality. Already said we want is machine independent measurements. Another concept that we are going to, or idea that we are going to use is we are going to be always interested what happens for large values of n. Typically we will not be trying to understand what happens when n is small. This knowledge or this understanding probably we have from the calculus that we learn, and we are going to try to abstract those ideas here. If you recollect from your calculus, then if you were trying to look at the limit of this ratio, so if I am going to look at this limit of the ratio, say 2n squared plus 2n plus 1 divided by n, as n tends to infinity, then we know this actually is 2, that we know from our elementary calculus. That is, for large values of n, that is as n is very large, this 2n squared, that is the numerator, is nearly behaving as your denominator. That precisely is what the asymptotic growth would mean. So, we are going to capture proportionality and we are going to capture it in asymptotic growth or for large values of n. So, our model that we intend to create will try to address these two key issues, proportionality and asymptoticness. So, if I look at the examples, a few more examples to motivate the notation. So, if I look at the first example, which is 100 into log n to the base 2, it is easy to compute or easy to observe using our standard school algebra, that when n is large, in this case we know large is if n is bigger than 1000, then 100 log n is less than n, that is this is true for n bigger than 1000. Very easy to observe that if n was 100, then the left hand side would be, so log n to the base 2 would have been 2 and the left hand side here would be 200 and right hand side is 100, and we know this is wrong, correct. So, what we are saying is if n is 100, this expression is not true, but if n is 1000 bigger than, then we know this expression is going to be hold true, and that precisely is what we said is what we are trying to capture is the asymptotic notion, that is for n large this particular expression is true or this particular thing is captured by in proportionality by n. So, that is the first example. The other two examples are similar, which basically tries to see proportionality and asymptoticness. The next equation is 70n plus 3000, which we know is true for n bigger than 100. Again, simple, some can be proved by school algebra that we have all of us already know. If I look at the third thing, which is similar, correct. So, the examples basically supports the motivation that we have in doing the analytical model, that is capture proportionality and asymptoticness of the problem. So, with this probably we should be able to now go to a concrete definition of what we have been trying to say up till now, right. So, the goal that we have for asymptotic analysis is something like 3n squared is similar to n squared, and key is the asymptoticness, that is to capture the essence when we have large input sizes of the problem. This brings us to the first important definition of the course. The definition basically abstracts all the fact that we have been saying up till now or being observing up till now. So, we have up till now, if you recollect, we have been talking about functions like 2n squared plus 3n plus 1, and on the other side we had function like n squared. So, if I look at now this, if I call this function as f and this as g, correct. So, I have functions f and function g, which are functions from set of integers to the set of real numbers. Right. So, these functions, the domain is natural numbers, the range in this case is natural numbers, but if I have more complex functions they can be even real number, that is if I say fractions or decimals involved or roots involved, then it can be real numbers, correct. So, definition is in general. So, we have a function from set of integers to set of real numbers. We say that f x is of order g x. So, we say f x here is of order g x if f x is less than or equal to c g x whenever x is bigger than or equal to k. So, I think there is a missed out this. So, this is c bigger than 0 if there are constants c bigger than 0 or c positive and k such that f x is less than or equal to c g x whenever x is bigger than or equal to k. Then we say f x is big O of g x. So, if you go back to the examples that we have been seeing here, now this precisely fits into the definition we have said. So, we have, so if my f is log n and your g is n, then your c is 100 and k is 1000, and then we can see that f x is actually less than, okay, c is say 1 by 100 is less than, I am just dividing by 100, is less than 1 by 100 into n for n bigger than or equal to k. Right. So, this precisely fits into the definition of big O, or alternately we can say that log n is of order n. So, that precisely is the definition of big O. So, it basically captures all the definition, all the observations that we have been doing up till now into a analytic expression. A few more examples which is going to be based on the calculus that we do. So, if I look at g n as say 17 n plus 5 and we want to find the asymptotic nature or asymptotic order for this particular function, then we know now by experience that it is going to be behaving like the highest degree that we have in this particular expression. In this case it is n. So, to verify that particular fact, we can use another expression equivalent to the definition, which again we had seen captures proportionality is we compute the ratio and the limit of the ratio. Right. So, rather than looking at a definition, I am looking at an alternative way of doing, showing that function is of big O of some other function, is you look at the ratio of Gn by Fn, find the limit of the ratio as n tends to infinity. If this is non-zero, then we say that Gn is of order Fn. And it is easy to observe here. I know if I look at this limit is 17, which is non-zero. So, this is say non-zero, then your function is of order n. Right. So, these are simple observations supporting our definition. We have a few more examples, more complex example. All these ideas of 1 and 2 can be generalized in 3. So, this is the general result, which basically combines the examples in 1 and 2. So, if we have a polynomial, so now Gn is a polynomial of order k, correct. The highest degree term in Gn is of degree k. Then this polynomial Gn behaves like n to power k or is of order n to power k. So, that is a general result which generalizes example 1 and example 2. Example which we know again from our calculus that we have learned in school, that exponential functions, if you look at the ratio of 2 to power n plus 4 n cube plus 16 divided by 2 power n, then we know this limit is going to be like 1. So, I am looking at limit n tending to infinity. This again we know from our school calculus. Therefore, we are going to say that this particular function g is of order Fn, where Fn is 2 power n. The last example is crucial in understanding. If I have just a constant number 1789, it just means this number is independent of n, right. So, this is a constant function independent of n. We will say that this function is precisely of order 1, or we will say this is a constant order, right. So, we will say either constant order or we will say of order 1. Right. So, these are just an example to illustrate the definition of big O. One another geometrical way of looking at the definition is, if I look at the two functions, right. So, if you are looking at f and g, what we are trying to say is that your f x is less than equal to c g x whenever x is bigger than equal to k. What does that mean is, your function f x, if I draw them on a plane, right. So, if I look at this is say my x axis, this is my y axis, and if you plot the graphs of these two functions, which we can do because there is a function from natural numbers to real numbers, then your function f x is less than equal to c g x. That means, maybe initially c g x is less, but after a stage which is x equal to k, this is always going to be bigger than this. So, if I draw graph like this, now, so if I look at this function, so this is my c g x and this is your f x. Now, if I look at this particular point which is k, now what do I observe is that for x bigger than k, that is all the elements to the right of x, your c g x which is here is going to be above f x, that is c g x dominates f x. So, the algebraic expression, the geometric understanding of it is that c g x dominates f x after a certain stage. So, that is a geometric interpretation of the big O notation. and which can be again very well verified in all these particular examples. Let us try to look at some more examples just to make sure that we understand the definition of big O. So, this is a problem where you are given an array of numbers or a sequence of numbers, and you are given a particular key element, and you want to search whether this particular element belongs to the sequence of numbers. Right. So, I have a sequence of numbers which are been stored in array in whatever order, not necessarily increasing or decreasing, and we are given a key x which is say 10, and we are trying to find whether this particular key is there in this particular sequence or not. The idea is simple. You start with the first element of the sequence and just scan as we go across and compare with the key. Again, we are just trying to find whether it is present or not. We are not interested if it is present how many times or not. The problem is simple, just to see whether the particular key belongs to this particular sequence. And in this particular case, we will start with the first element, compare it with 10. If it is yes, we are just going to return the index. If not, we will update the counter and keep on doing this. Now, we will compare the next element which is 3 with 10, answer is no. So, we will increment the counter and keep on doing this up till we reach the end of the array, that is until j becomes n. As j becomes n, the algorithm will terminate. So, if the key is present, it will return the index of the array element. If not, it will return that the key is not present in the array. Now, we can very well see that the number of comparisons that this algorithm is going to do to say yes or no is going to depend on the input. For example, in this particular input, since x equal to t was not present, one has to do all the computations 1, 2, 3, 4, 5 to conclude that the key is not there in the sequence. Whereas, if you had 10 right at the beginning, then as soon as you would have started searching, you would have found 10 and stopped the process. Right? So, this is a very crucial observation which supports the fact that we had seen earlier, that number of steps that your algorithm takes can depend upon what is the arrangement or what is the instance of your input. The same point we had observed when we were looking at the sorting problem. There we could not concretize it, here we could actually write down a concrete example. Right. So, for example, in the first case we had to do 1, 2, 3, 4, 5, 6 operations and had to say no, whereas in the second case, in the first instance only you could say that the element is present in the sequence. Right. So, this brings us to a very important point in our analysis. Is so, when you are typically looking at an algorithm, let us try to illustrate or try to understand this with a problem that we do face in real life. Suppose you have to move from, suppose some XYZ person is supposed to catch a flight from an airport and he stays probably say 20 kilometers away from the airport, and flight is say at whatever time 3:30. Now, the person has to decide how much before that he has to start, so that he reaches well in time to catch the flight. That depends in this case upon the experience that the person has about that particular city. And usually the way the person or a human is going to compute is, he is going to look at the worst time that he is going to take to reach that, assuming that there are traffic jams, there are traffic snags, there are construction work going on, what not, and decide how much before he should start. He would rather not decide. For example, if it was a Sunday morning, all the roads would have been empty and he would take probably much lesser time to reach the airport. So, there are two key things that we are trying to observe. One is the worst case scenario, that is what is the worst case that is required, and what is the best case. We already have seen in this particular example an example of the worst case where we had to scan the complete array to say yes or no, and in the second example, right at the first step you could say yes and stop. So, this brings us to two key points that we are going to look at. So, time complexity and if there are if statements brings us to two important cases that we are going to look at. That is the best case, that is what is the best case of your algorithm, and the worst case is in the worst case scenario, that is what is worst, that is given any random input. Okay, I know if I do this many steps I will solve the problem. You are not really worried about what is the best case of your problem. So, already observed in this case that best case is just one, that is the key that you are trying to search is right at the beginning, and the worst case is that the key that you are trying to find is not there in the sequence at all, or the worst key or it is not there, in which case again you still have to scan the complete array or the complete sequence. So, that brings us to always, so any algorithm typically you would be always interested in worst case, because that guarantees that if I do n computations I will solve the problem. Best case scenario probably you would like to know, but not going to be so important as worst case. Worst case guarantees that I do this much work and I am going to finish. Another crucial factor as we go ahead that we will deal with is what is called average case. As we seen, the best case and the worst case depend upon the arrangement of the numbers or a particular instance of a problem. Right? One instance led us to the worst case, one instance led us to the best case. What happens in general, that is if I have a random input, and that is what an average case would mean. Right? So, average case is not an average of worst case and the best case. An average case would mean if I have a random input, that is when I say a random input means every input has an equal chance of being a instance of a problem. So, as we go ahead we will also try to deal with average case. So, in practice usually best case is not so important, worst case is important because this gives us guarantee about solving a problem in a certain amount of time, and in practice we also are interested in average case. In real life it is not always that we are going to face a worst case. It can also mean that we always are going to have random inputs, and we would like to know what time it takes in that case. Right? So, that would be average case, which we will define as we go ahead in this course.